Hello, welcome to a tutorial video on Conic Sections. In today's video, we will talk about the definition of Conic Sections, the various types of Conic Sections, and their real-life applications. So, Conic Sections is one of the most fascinating topics in geometry. And at the end of this video, you'll be able to know the different types of Conic Sections and their real-life applications. Also, you'll be able to solve equations involving the various types of conic sections. Now, what exactly are conic sections? Imagine slicing a cone. Yes, a real cone like an ice cream, but with that an ice cream shape looks like a cone. So imagine slicing a cone. That's a real cone like an ice cream cone, but with a flat surface at different angles. The shapes that you get from these cars are what we call the conic sections. So you can have a shape like circle, an ellipse, parabola, and a hyperbola. And these are the ones we will talk about in our subsequent sections of this particular video. But the interesting part of it is that these shapes are everywhere around us, from satellite dishes and car headlights to bridges and planet orbits. Even the path of a thrown ball follows a conic section. So as I said, in this series or in this particular tutorial video, we will explore the definition and formation of each conic section, their equations and properties, and of course a real life applications you never knew were math related. Now, don't forget to like, subscribe, and hit the bell icon so you don't miss any episode in this particular tutorial video on conic sections. Well, now let's get started. What are conic sections? Conic sections are the curves formed when a plane intersects a double napped cone. So when we talk of a double napped cone, then we are really referring to a cone with two identical parts pointing in opposite directions. So if you can clearly see here, we have one cone here on top here, then we have another cone at the bottom part here. So if you have a double napped cone, then this cone it's called a double napped cone. Okay, so that's what we are trying to talk about here. When a plane intersects right circular cone, a conic section is formed as per the definition given here. So what we are trying to say is that if there is an intersection of a right circular cone, then a conic section is formed. So the intersection happens between a plane and a cone. But in this case, we will talk about a double napped cone. Now, when we talk of a double napped cone, as I said earlier, a double napped cone is a cone with two identical parts. So we have one part here, then another part here facing each other or pointing in opposite directions. So one is pointing upwards here and one is pointing downwards here. And this is the vertex of the two cones. We will make use of the vertex of the two napped cone later in this video. So clearly you can see that there is an intersection of a plane and a double napped cone. And depending on the position of the plane and the double napped cone will determine the kind of conic section that we will have. So also depending on the angle, the intersection can also produce different types of conic sections. So either the angle or the position of the cuts, the intersection produces four basic shapes. These are the circles, the ellipse, the parabolas, and the hyperbolas are shown in these figures. Now let's talk about them one by one and their real life applications. Now let's talk about the first one. In general, conic sections are used in architecture and engineering. For example, bridges and satellite dishes. Also in astronomy, we can talk about orbits of planets and their comets. In technology, we can also talk about signal focus in satellite dishes and flashlight beams. In our daily lives, we can talk about eyeglass lenses, microphones, water fountains, and those stuff. These are real life applications of conic sections. Now, let's talk about the first type of conic section formed by an intersection of a double napped cone and a plane circle. So, a circle is formed when the plane cuts the cone perpendicular to its axis. So, as you can see, there is an intersection of the plane and the cone, but the plane cuts the cone perpendicular to its axis. Okay, so that is perpendicular to its axis. We are talking about the cone which is perpendicular to its axis. Now, in real life applications, first of all, before I talk about the real life applications, let me talk about the definition of what I've just given here, or the explanation, more explanation of what I have just given here. So what it means is that there is a horizontal cut through one nip. So, and that is what is happening here. There is a horizontal, you see, this type here is a diagonal cut here. But for the circle, it's a horizontal cut between the plane and one of the double napped cone. So when there is an intersection of that sort, then the conic section that's formed is a circle. And that's why I said that the circle is formed when the plane cut the cone perpendicular to its axis. So you see that the cone is perpendicular to the axis of the cone. Yeah, the plane cuts the cone perpendicular to its axis, and that is what is exactly happening here. And for that matter, the plane is horizontal. There is a horizontal cut between the plane and that of the one double nap cone. In this case, we are using the bottom one here. So when that happens, there's a conic section which is circle created. One thing about that, uh, one thing about this conic section is that all the points on the circle are equidistant from the center, and that's one of the properties of the circle formed between the intersection of the plane and the cone. Now let's talk about some real life applications of this conic section. That is a circle. Talk about wheels of barrels or wheels of tires of cars. We also talk about ties, clocks, and CDs, manholes that are normally designed to be circular so that they don't fall in. We can also talk about GS in mechanical systems. These are examples of the real life application of the conic section circle. Now let's talk about the next one, which is I'll come back to the parabola. Let me talk about the ellipse. So for the ellipse is formed when the plane cuts the cone at an angle. So when there's a plane, there is an intersection of the plane and the cone. By this case, the plane cuts the cone at an angle. When that happens, there is not a steep enough to go through the base of the cone. So it doesn't go through the base of the cone. It's slightly lower than the base of the cone. So when that happens, the conic section that form is an ellipse. Now let's talk about some of the real life applications of the conic section ellipse. Orbits of planets. So this looks like an orbit of the planets or the moons and satellites. Can also talk about the design of elliptical gears and lenses. Also in medical procedures, we can talk about elliptical reflectors. So these are some of the real life applications of the ellipse. Now let me talk about the hyperbola, then I'll come back to the parabola again. So for the hyperbola is formed when the plane, so this is the plane as usual, but this case, the plane cuts both of the double nap cones. So it cuts the top part, it also cuts the down part here. So a hyperbola is formed when the plane cuts both naves of the cone at a steeper angle than the side of the cone. So it cuts the cone at the at both naves of the cone, but here at a steeper angle than the side of the cone. So when that happens, the conic section that forms at the top and the down parts of the cone is called a hyperbola. And in navigation system, GPS and radio signal triangulations, a hyperbola is also used. Some of we have also lenses in telescopes and microscopes, which are also hyperbolic in nature. Now, let me talk about the first one, which of course I skipped, the parabola. All right, now the parabola is formed when the plane cuts parallel to the slant of the cone. So this is the slant height of the cone, the side here. Okay, now let me use this one. So this side of the cone is called the slant height of the cone. So when there is an intersection of the plane and the slant height of the cone, this case, this side, when the plane cuts the cone at the slant height of that cone, then the conic section that forms is called the parabola. In real life applications, parabola can be in a form of satellite dishes and also radio telescopes. We also have car headlights, example of real life applications of parabola, car headlights and flashlights. Now, suspension of bridges and also flashlights are also a typical example of real life application of parabolas. So when they look, the shape of a suspended bridge or cables that is lowered on bridges forms a parabolic shape. Also, when you throw a ball, for example, when you throw a ball to a player on the other side, the projectile motion of that thrown ball is also looks like um, it's also a parabolic in nature. For example, let's say there is a player here and you throw a ball, so that projectile motion made by the ball is parabolic in nature. So these are some of the real life applications of the various types of conic sections and um, yes, the various types of the conic sections and how they are formed by the intersection of a plane and a double napped cone. All right. Now, another way of identifying conic sections is the or identifying the kind of conic section formed when a plane intersects the right circular cone is to assess the angle formed between the plane and the axis of the cone and compare it with the angle made by the axis and the cone and the vertex. So now when we talk about the axis of the cone, then we are talking about this line. That's vertical line here. This is the vertex, sorry, the axis of the cone. These are slant heights of the cone. And then this is the where the two double nap cones meet is the axis, the vertex of the cone. All right. So here we are talking about the angle formed by the axis and the cone, and then angles formed by the axis and the plane. So we are saying that when the angle formed by the axis and the cone at the vertex is alpha, so we are representing the angle formed by the vertex and the cone, or with one side of the slant height of the cone as alpha. Now we are also representing the angle between the intersecting plane and the axis of the cone as beta. So we are representing the intersecting plane, the angle between the intersecting plane and the axis of the cone as what beta. So a case like what we have here, beta is half of 180. That is 1 pi on 2, which is 180 on 2. So if we have the angle beta to be 90 degrees, then we are saying that that particular conic section is a circle. Again, we are saying that if alpha, that is the angle between the axis of the cone and the one of the slant edge or the slant line of the cone, if that angle is less than the beta, the angle over here, then we are saying that if that angle alpha is less than beta, then it's also less than 90 degrees. Clearly, we can see that this angle, particular angle here, now let me clean this and rewrite this one again. You could see that from here, the angle over here is not equal to 90 degrees. So beta is less than 90 degrees. This angle over here too is less than 90 degrees. This angle alpha is less than 90 degrees. And for that matter, this pi on 2 is the same as 180 on 2, as well as the same thing over here, 180 on 2. So we are seeing that if the angle alpha is less than beta and is also less than 90 degrees, then the conic section form is an ellipse. All right. Now we have another scenario here. We have the angle alpha here. There's an angle beta here. Now we are saying that if alpha is equal to beta, then that conic section is a parabola or is parabolic in nature. Of course, that is true. So by the alternate angle property, we could see that alpha here and beta here are all equal. Now the next thing that we want to talk about is also the last type of conic section, which is hyperbola. Now we could clearly see that angle alpha is greater than 0, but angle alpha is less than the angle over here. The angle alpha is less than, the angle beta is less than alpha. So when that happens, the smaller angle over here, which is beta, when that happens, then we are saying that that particular conic section is a hyperbola. So these are one way of identifying the kind of conic section formed when a plane intersects a right circular cone using the angle approach. Now we want to talk about parabola as a first part of the conic sections. Now, when we talk about parabola, in definition, we are saying that parabola is a set of all points in a plane that are equidistant from a given point, a given line, which is called directrix, and a given point, which is focus, not on the line. Now, the given line is called the directrix of the parabola, and then the given point is called focus of the parabola. Now, in this definition, we are saying that all the sets of points are equidistant from a given line. So all sets of points here are equidistant from a given line, and that given line is called the directrix. Again, true, it means that this is a set of points. This parabola that you see here is a set of points. Set of points, set of points, set of points, and a set of points here. So the definition says that a parabola is a set of all points in a plane that are equidistant from a given directrix. So all these points that you see here means that from the focus to any point here, is the same distance from that point to the directrix, and that's what you are trying to mean here. Now let me take it again. From the focus to any of the set of points, let me say there is a point here. There is the same distance from that set of points to the directrix. So no matter how we trace the line from the focus to any of the set of points, it will be the same distance. So again, if there is a set of point here, then the distance from the focus to that point is the same distance from here to here. Alright. So the definition continues to say that the given line is called the directrix of the parabola, and then the given point is called the focus, and that point is not on the directrix. So that is one thing we should take notice of. The given point is called the focus, but that focus here, which that is the point here, is not on the directrix. Now we are also saying that the parabola is symmetric about the line that passes through the focus. So there is a line here that passes through the focus of the parabola, and that line is called axis of symmetry. And that line also divides the parabola into two equal halves. So one part from here to here. So let me call this one 0 to A. There's another part which is at the bottom here. So 0 to B. So you see that the line of symmetry here has divided the parabola into two equal halves. So let me call this one as part P and part Q. So this part from here to here is the same as from here to here. That's why we are saying that the parabola is symmetric about the line that it passes through the focus at a right angle to the directrix. Okay, so this line is called an axis of symmetry, simply axis of the parabola. And the axis meet the parabola at a point called vertex. So the point where the axis of the parabola meet is called the vertex of the parabola. So this part here is called the vertex of the parabola, and this point here is called the focus of the parabola. So that is one thing we should notice of. Now on this same diagram, you can clearly see that from the focus to the vertex is the same as from here to here too. So from the focus to the vertex of the parabola, if it is P, then from the vertex of the parabola to the directions is also equidistant from equidistant from the vertex. That is from the focus to the vertex is the same distance from the vertex to the directions. All right. Now let's talk about some of the general or geometric properties of parabola. So we've already talked about this, that if the distance between the vertex and the focus is P, then the distance from the focus to the vertex and the distance from the vertex to the directrix will be the same as all P. The distance between the vertex and the directrix is equal to the distance between the vertex and the focus. Therefore, the distance between the directrix and the vertex is also P. We've already talked about this. Now, the distance between the focus and the directrix is 2P. All right, so if from here to here is P, and from here to here to is P, then it means that from the focus to the directrix is 2P. All right. The parabola also passes through the corners of a box that extend from the vertex to the focus along the axis of the symmetry and extend 2P units above and 2P units below. All right, so what we are saying that if you draw a shape like a box from the directrix to the parabola, something like this, the same thing that we draw from the box, then it means that if here is P and from here to here to is P, then the whole of this side is 2P, and it's the same as what we have here. So from here to here to is also 2P. If from here to here to is also what 2P, and from here to here to is also 2P, and that is what we are trying to see. So the first part of the box is this side. It is of equal distances. So if here is 2P, then here to be 2P, here will be 2P, and here will be 2P. The same thing as this one, same thing as this, and that is what we are talking about here. Now let's talk about the standard equation of a parabola. Now we are seeing that the standard equation of a parabola is the simplest if the coordinate axes are positioned so that the vertex is at the origin and the vertex is at the origin, and the axis of the symmetry is along the axis, x-axis or the y-axis. So when the parabola coordinate axes are positioned so that the vertex is at the origin and the axis of symmetry is either along the x-axis or the y-axis, then the equation of the parabola is very simple to get. So we can have a parabola where the parabola is the vertex is at the origin and the axis of the symmetry is along the x-axis. That way, getting the equation becomes very easy. In other words, you can have the parabola in this way, where the parabola is at the vertex is at the origin, and and then it's also having the axis of the symmetry along the y-axis. In that case, if we have any of these orientations of the parabola, then we are saying that the standard equation is very, very simple to get. So we can also have the parabola to be also facing the side, but the vertex will be still at the origin. We can also have it in this way too, and the vertex could still be at the origin. It means that we can have one, let's say 2, 3, 4. What does it mean? It means that we can have 4 possible orientations that can provide us with 4 standard equations of the parabola. So if the parabola is facing the positive side of the s, as the s is 7, s axis is 7 as the axis of the symmetry, then you can have one equation there, and also have one equation, one equation, one equation. In all, we can have 4 possible standard equations of the parabola, because these orientations are the standard positions of the parabola. All right, now let's take the first part. Given that there is a point on the parabola, as I said earlier on, there is a point here, and that point to the vertex of the parabola is the same as from the vertex to the directrix. Of course, if we have a point, another point, which is on the parabola, let's call this point as xy, as indicated over here already. Okay, it means that from the focus to the point is the same as from the point to the directrix, and that there is an angle 90 degrees created by that line here. All right, so if we have a point on the parabola, then that point assumes values of coordinates x and y, because there is a value that can be traced from the that can be traced from the x-axis, and there is a value that can be traced from the y-axis, and that's why we have coordinates to be x and y. Now for the origin, because the parabola is at the origin, it means that the coordinates of the vertex is 0, 0, and that is what we have here. And for the focus, because we have not numbered our axis, we are representing the x coordinates of the focus by the letter P. And if the focus is on the x-axis, it means that the y-axis, the y coordinate is 0. There is no value for the y coordinate because the focus is on the x-axis. For that matter, there is no value for the y coordinate. That's why you have P0 here for the focus. So if it were to be here, then if the focus was to be here, then we could have had it as negative P, because here is the negative values of x, so we have negative P0. If the focus was to be here, we would have had the focus to be 0, positive P. And if it were to be here, we would have had it to be 0, negative P, because these are the negative parts of y. Okay. So back to this. We are saying that there is a point that is located on the parabola of focus P0. Then the directrix is equal to x equals negative P. Of course, if we have our directrix to be negative P, and if here is equal to this side, and here is y, then we can clearly see that x is also equal to negative P. Y is equal to y. Then it means that x is also equal to negative P. And the vertices at the origin are shown below. Now, what does that mean to here? It means that from the distance F to Q is the same distance from Q to D, as I said earlier on. The distance from the focus to any of the set of points on the parabola is the same thing from the parabola to the directrix. So if we have F to Q to be the distance from here to here, then it means that this distance is equal to Q to D, and that is what we are seeing here. So using the distance formula, then we have root x minus p all squared plus y squared is equal to x minus p all squared. So when we um, take square, when we square both sides, or we take square on both sides, means that this one will cancel this and this one will cancel. Don't forget that these F and Q are represented with coordinates, and that's why. So here we use the distance formula y2 minus y1, or y1 minus y2, the same thing that we get. So y1 minus y2 all squared plus x1 minus x2 all squared. So that's why we had these things over here. So when we take square on both sides, then it means that we are going to remove the square roots, and that will give us x minus b all squared plus y squared equals to s plus b all squared. So when we further simplify this is a binomial expansion. So we are going to have x squared minus 2px plus p plus y squared equals to x squared minus 2px plus p squared. Sorry, this one is supposed to be minus. So when we rearrange this, means that this one, when this one comes here, it's going to be positive 2px, and it will cancel out, and then we will be left, and then we have our y squared to p squared to be also, this one is supposed to be p squared, sorry. So this p squared will also cancel out. Then you have our x squared to also cancel out. Sorry, this one is supposed to be plus, of course. Sorry. This one is supposed to be plus. So it means that we are going to have negative p minus negative px, negative px, and that gives us negative. Yeah, so that gives us positive 2px over here. So if this one cancel out, and then this one is p squared, so this one cancel out, then it means that our y squared, we will send this one here, and it will be positive. So if we send this one here, it's going to be positive 2px, and that gives us y squared to be equal to 4px. So this is the equation when the parabola is facing this side. Okay, so the nature of this parabola is that if we take a critical look at this parabola, it shows that the vertex is at the origin, of course, that is here. And the parabola also opens to the positive x direction. So all these values are from here to here are all positive values of what? The x-axis. For that matter, the parabola opens to, it opens to the positive x direction. And also the parabola is also symmetric about the x-axis. So the x-axis is the line of the axis of symmetry. So that is another one thing here. Now, if the parabola is open to the negative x directions, then the equation, we are going to have our y squared to be negative 4px, and that's how we came about all this one too here. So as I said earlier on, if the parabola opens to the negative x direction, it means that the focus is going to be negative p0, as I said in our earlier video. And for that matter, x will be equal to positive p. So you have here to be negative when we use the distance formula y minus y1 minus y2 all squared plus x1 minus x2 all squared. So using the distance formula, we will get this. Now when we simplify, you have y squared to be equal to negative 4x. So the easiest way to get this formula is that when the parabola is open to the positive x direction, the equation is equal to y squared is equal to 4px. And if the parabola is open to the negative x direction, the equation becomes y squared is equal to negative 4px. So this is the easiest way to get the equations of the two orientations. And now let's talk about the nature of this parabola. So the vertex is at the origin as usual. The parabola is also open to the negative x directions. And then the parabola is symmetric about the x-axis. Now let's talk about a case where the parabola opens to the positive y direction. So the only changes that makes is that in the first two orientations, we had the equation to be for the positive x direction, we had the equation to be y squared equals 4px. And this is for the positive x direction. In the negative x direction, we had the equation to be y squared is equal to negative 4px. Now we are talking about positive y direction. So the only changes that takes place is that here we will not get the y squared here, we get x squared, and here will be 4py. So if it is open to the negative y direction, it means that we are going to have our equation to be x squared equals negative 4py. So that is what we have here. I don't want to waste time on this. So the nature of this parabola is that the vertices at the origin, the parabola opens up the positive y-axis, and the parabola is symmetric about the y-axis. So this side, the y-axis divides the parabola into two equal halves. Then the last orientation, where the parabola opens to the negative y directions, it means that we are going to have our equation to be x squared equals negative 4py, and that is what we have here. So that is the last orientation. Now let's talk about the nature of this parabola. So the nature of this parabola is that the vertices at the origin, the parabola opens down, that is the negative y-axis, the negative y-axis, and the parabola is also symmetric about the y-axis. Thank you very much, and don't forget to subscribe to our channel. So in this example, we are to find the equation of the parabola with the vertices at the origin, and the following foci. So in the first example, the focus is 0, -2. So it means that if the focus is -2, then it means our focus is in the form of f0 -p. In that case, it means that our parabola is open to the negative direction of y. And for that matter, our equation is x squared is equal to negative 4py. If that is the case, it means that our y is equal to negative p. So if y is equal to negative p, then it means that p is also equal to negative y. Okay, so if p is equal to negative y, from the focus, y is equal to -2. So therefore, our p is equal to negative into bracket -2, and p is equal to +2. So that's how we came about this. So if p is equal to +2, then we are going to substitute this value here. So if p is equal to +2, our x squared is equal to -4 into bracket +2 times y. -4 times +2 gives us -8. For that matter, our x squared is equal to -8y. So that's the first one. And the second one too, we have the focus to be 5, 0. So this means that the parabola is open to the positive direction of x. For that matter, our equation is y squared is equal to positive 4px. So if our x is equal to p, then it means that p is equal to 5. From here, our x is 5 and y is 0. Since the parabola is open to the positive direction of x, our y is equal to 0. So if p is equal to 5, by direct substitution here, we are going to have y squared equals 4 times 5x. So 4 times 5 gives us 20. For that matter, our equation is y squared is equal to 20x. And for the last one, we have our y's, the focus to be -1 on 2. It means that the the parabola is open to the negative side of what? The negative direction of x. And for that matter, our p is equal to -x. And if p is equal to -x, then our p is equal to negative into bracket -1 on 2. And that gives us p equals to 1 on 2. So if p is equal to 1 on 2, by direct substitution here, we are going to have our y squared equals -4 into bracket 1 on 2x. So this one, we simplify, we get -2. So negative 2 times x gives us negative 2x. In this case, our y squared is equal to negative 2x. So these are the solutions for our first example on parabolas. Thank you, and don't forget to subscribe to our channel.